started a little early, so you caught me off guard. I was getting ready here, but
Yeah.
Here we go. So while he's pulling that up, I'm Julia Wellner. I'm a professor at the University of Houston. I am in Earth and Atmospheric Sciences. I study sediments. Yeah.
Just do the inner.
I will. Okay. So I know that is not the background of most of you. So what I'm going to do today is give a sort of short, simple overview of some of the work that we're doing in the Houston area. So even though it is not your exact scientific expertise, I hope it's interesting as a affiliated science, especially because it is in your neighborhoods. So, here we go. So I'm going to actually present 3 vignettes that hopefully build to a combined set of conclusions here. And only the latter 2 will actually specifically be about Hurricane Harvey. I'm going to start with the modern Brazos Delta and use that as an example to show you how we study modern sediments. And from there, we're going to talk about the San Luis Pass tidal delta, which is actually what is shown in the photo, and that is how we study it, by weighting. And then I'm going to move on even more to the urban sediments that moved during Hurricane Harvey. Because I am a professor in a research university, most of what I show you is actually done by my students. So I would just like to highlight that the first section of this was done by my very first master's student, Derek Rice, who went on to Rice Energy, which carries his name. The second section is by a PhD student named Carolina Ramon, who now works for Occidental in exploration. And then the third section is by Andrew Stearns, who is my very recent master's student, who is now working at TGS. So starting with Hurricane Harvey, just to make sure, starting with the Brazos Delta, in this beautiful map of American drainage systems, you can see the Mississippi is by far dominant. And then the Brazos River is about 2 orders of magnitude smaller than the Mississippi in drainage basin size and volume. And its delta sits out here, not far from us, not far from Freeport. And we can see its delta protruding out here into the Gulf of Mexico. We studied this through a range of methods. Primarily what I'm going to show you today is core data. We collect cores in a variety of ways. In this particular project, I'm showing you this onshore vibrator core, as well as the core warehouse that is now stored. So we've actually utilized many decades worth of cores to collect this. So, as many of you may know, the Brazos River was actually diverted in 1929. So the Brazos River is not a very natural delta. It is a delta that was diverted in order to prevent Freeport from filling up with sediment. So in 1929, the Army Corps of Engineers diverted the river. You can see the diversion point. You can drive over it today. You can drive over both of these sections of river, and they're labeled Brazos River, even though there's 2 separate entrances there. And they did that because the Brazos River carries so much fine-grained sediment that Freeport was shoaling. That provides a natural laboratory for us to study. If we know that delta started to form in 1929, it becomes a perfect laboratory to understand delta growth. If I wanted to study the San Jacinto or go to Anahuac or the Mississippi, anywhere else you don't know exactly the starting point of the age of the sediments. And because this was diverted, we're able to study it in a lot more detail. And so many people have, over the last 30 or 40 years, focused on studying the Brazos Delta. And everybody wants to study the sand, right? That's the same is true if you're a geologist working in Utah and hiking in the mountains or the cliffs. Everybody likes to go out and look at sand as a geologist. It's easier. You can see it. It makes cliffs. It's easier to measure in the laboratory. I mean, a whole bunch of reasons that people focus on the sand. And so there were many studies of this part of the delta, but virtually no one was out here looking at the clay distribution. We thought that was a worthwhile endeavor, and we had a very simple hypothesis that there would be two distinct clays, that there would be the longshore transported clays that were up dip of the river, and then Brazos clays that were down dip of the river. So this is a simple prediction that we would have the gray clays up dip and the red clays down dip. The reason this was a perfect experiment is that the Mississippi River, which might be far away, but it's really big, so it carries a lot of sediments, carries a distinctly different chemistry than the Brazos River. And so we could come out here and look at the local sediments. And so here in this image, I can show you, I guess I have to use this pointer here, the cursor. So if we're looking at the clays that are transported by longshore drift from the Mississippi River, they are dominantly smectites, that's the gray clay, and that represents the drainage basin through the Mississippi. And they are coming across because that is the dominant direction of longshore drift. Clay number 2, the Brazos clays, the red clays, are dominantly illite and kaolinite. And that's why you see that red color if you go out to the Brazos. It's got a distinctly different mineralogy than the rest of the rivers from here to the east. And you can see that in the water, you can see that in the sediments. And if I take you to look at the offshore cores, we can see this really distinct pattern, but not as we thought we would. So this is a chance, I'm trying to show you our simple predictions led to a much more complicated understanding. So here's one of these cores taken from offshore. This is actually an older one of the cores. This is taken by Rice University, which is where I did my PhD. And in this one, what we see are these distinct layers of red clays with the intermittent gray bands. In sedimentology, we use red and gray to mean precisely these colors here. And so we have red punctuated by gray. Remember that the red is coming locally from the river and the gray is coming long distances from the longshore drift from the Mississippi. And so here is a schematic of this study area showing where the Brazos River is coming out here. We have a cluster of downdrift clays and a cluster of updrift clays and cores. So I'm going to just show you that these are the real data sets. Now we'll zoom in and look at the simplified versions. So here are just two individual core examples. Let's start with the downdrift side on the left here. So this is one of the cores that is south or west of the Brazos River delta. And it's kind of all homogeneous looking. Kind of gray, kind of red, no particular preference there. And no distinct layering. And what we have in the updrift side is these distinct red bands and gray bands. Red, gray, red, gray, red, gray. And that's shown in the core photos. It is shown in our hand-drawn lithologic logs. And just to be clear, while I'm only showing you the simplified core versions here, we do a range of analyses in the lab to confirm the grain size distributions. In my lab, we use laser particle size analyzer, and all of the clay chemistries are done with XRD. So we see these distinct patterns where the updrift side is the distinctly layered one. So let's think a little bit about how that could happen. This is a diagram of longshore drift and river discharge. And so on the x-axis along the bottom, we have time going from left to right. And on the y-axis is discharge coming out of the Brazos River. And so the higher the bar, the higher the river discharge. In red are times when we have, let's start with blue, sorry. Let's go to blue. Blue is the normal longshore current. The longshore drift is doing its thing. It's bringing sediment from the Mississippi River to the Brazos River, going in the normal direction like it always does. But if you notice, there's a lot of times there of high discharge from the river that are shown in red instead of in blue. And those are times actually when the longshore drift has flipped. And the longshore drift is going, instead of from Mississippi to Houston to Corpus, it's going the opposite direction, from Corpus to Louisiana. So these times of high discharge from the river correlate with the reverse in longshore drift. Let's look at one more background idea. El Nino and La Nina actually have a big impact on not only the water discharge, but the sediment discharge out of this river. This is a paper by Carmen Fraticelli that was published showing how the Brazos River itself has responded to El Nino and La Nina cycles. In Texas, on the left, we can see that El Nino conditions, like we're entering into right now, correspond to active storm tracks, right? We should get plenty of rain, plenty of storms. That's the standard El Nino here. Of course, it's variable. In the La Nina, which is the preceding cycle, Texas should be relatively warm and relatively dry. And these periods, of course, shift, on 5 years or so. And they correlate to rainfall, right? El Nino is wet. Then they correlate to sediment flux, not just with rainfall, but also with how much is the vegetation surviving, right? Vegetation holds sediment in place, and when it dies, the sediment comes out into the river. And so we can think about the pulses coming down the river and how they respond to El Nino cycles. So if we look then at an example core, we can see that there are pulses through here. Updrift cores, updrift again meaning this side of the Brazos, where we are now, typically show about 15 to 25 high discharge events. And we know that this started in 1929. So we can tie that to these pulses of sediment are going to come down the river. And the river is not at all evenly flowing. It's not evenly carrying sediment, but it's sending it out in pulses down the river. The layering that occurs only on the updrift side is because of that correlation between the big pulses of sediment come down in the reversals of longshore currents. So I told you this was just to get us primed for Harvey. So the conclusions here, and this is conclusions one of 3 for you, are that thicker and more uniform deposits of Brazos clays are found in the updrift environment, correlating with reversals of longshore drift during northerly storms and river flood episodes. More mixing of facies is found in the downdrift environment. Most deposition throughout delta history is rather than just during individual floods. So this story is giving us this pulsed nature. The sedimentary record is not a long, gradual record. Geology does not tell us the history of Earth in continuous time. Rather, it's giving us this pulse and then a long gap, and a pulse and a long gap. The modern setting, I'm barely a geologist, I study how sediment moves in real time. This gives us the ability to look at those pulses. So, remembering that that is the nature of the sedimentary record, let's think about Hurricane Harvey. So, Hurricane Harvey, as you probably remember, at least those of you that lived here in 2017 should remember, was a major storm. It wasn't actually a hurricane impact on Houston, but rather a rain impact. The storm itself made landfall in late August, much farther to the south, but then it drifted and wrapped back around the Houston-Galveston region. And so this storm track itself here is just a depression as it wraps around us. But it is that tropical depression that carried all of that rain. So, I mean, we don't often measure rain in meters, but 3/4 of a meter of rain fell in our area. The epicenter of that bullseye is actually to the east of Houston. That was approximately our average annual rainfall that fell over those 5 days. And another way we can think of it is as 11 cubic kilometers of water. That probably had an effect on our area. Okay, let's think about it a little bit. So back to the methods of what else do we do for this particular study. We are working with a kayak. We don't kayak for our studies, rather we wade. I showed that to you on the agenda slide, that we walk across the delta in shallow water, but we tow a kayak behind us to carry our stuff. While doing this, we are also taking samples. We are measuring water depth, actually using a rod and then correcting that for the tidal change. And I do have, in addition to the kayak, I do have a small pontoon boat where we take grab samples in water just slightly deeper than we can walk. Unfortunately, there's usually a little bit of an area where it's just a little too deep to walk and a little too shallow to use a pontoon boat. But we do the best we can. To do this work, we are doing water depth. We measure the ripple height of individual sand ripples, the wavelength, the geometry, and the progradation direction, as well as collecting samples. Our pontoon boat, it's a research vessel, so we give it a name. The RV Mishipeshu. Mishipeshu is a water cougar. So it's just a party boat. But it sounds a lot more official if we give it a name. In addition to this, we do shallow geophysics, and shown here, this is just the 3.5 kilohertz chirp system, so a towed, very shallow seismic, and my students working out here one summer. In my lab, we do a range of proxies. Shown in this case is just a bunch of individual sand grains. In the white box there, that is a Silas laser particle size analyzer. So it has 3 lasers inside to measure the refraction off grains, and we tell the size. And then it is connected to a microscope, and that microscope takes a series of photos. As every sand grain passes through the microscope, we take a photo. That photo is digitized. We run a little MATLAB code. We're trying to switch to Python, but right now it's still MATLAB to do a Fourier transform of the roughness coefficient of each individual grain. We also do SEM of these grains. Why look at individual sand grains? It helps tell us about transport mechanisms. It tells us the age of the particles and how they have been moving. Have they been moving in the water column, or are they moving along the base? Is this a popular thing to do? Well, I think people tried maybe in the 70s or so to use grain shape. And while it worked, it took forever, right? It takes a long time to measure the roughness of a particle that's 1 millimeter in size. And so it died out for a couple decades, and it has come back now that it can be done through this automated process. So we were working down at San Luis Pass. San Luis Pass is just at the end of Galveston Island right there. So it is the natural inlet between Galveston and Follett's Islands. And so we were out there collecting a series of sediment samples, doing all those things I was showing you. That was our data set to start with. Working out there, we are walking and measuring the individual ripples through this area, and we were able to find that there's the distinct grain size variability between the delta and the rest of West Bay back here. So you can see this is the sandy front of Galveston Island. This is the back shore through here. It's always dangerous to use somebody else's computer, sorry. This is the sandier part of that tidal delta itself, and this is the finer grained bay area of West Bay. We can find a range of correlations. This is why we were doing this project. We were looking at relationships between particle size, ripple height, and water depth. The whole purpose of this study was able to build these correlation plots so that we could go back in time. And if we find other deltas in the rock record, say from 60 million years ago, and we want to know if it was a tidal delta like San Luis, then we could look at that grain size ripple relationship. In that work, we found that the ripple wavelength was the best proxy for water depth, and that was a great tool for looking at the rock record. But we only had those 68 samples. And we were only halfway done when Harvey hit. So this study was not planned for looking at Harvey, but obviously we had to take a break when Harvey came, and we only had half of our samples done. And so being a good earth scientist, we wrote a grant to the National Science Foundation while it was still raining, and received what is called rapid funding in order to continue the study immediately following Harvey. So serendipitous, at least I tried to tell the PhD student that it was not a crisis in her project. So what could we find with this? There is a distinct shift in the grain size pre and post Harvey. That's interesting in itself, that we can think about how the size shifts over time. The water depth also shifted over time, so it became deeper and finer over time. So I'm going to look at this summary plot here. I think this shows it nicely. So you can see in the map, this is not a map, it's Google Earth image. Okay. So right here you can see the bridge. This is Follett's Island. This is the bridge across, and that's of course where we show us walking through there. This is Galveston Island here. In the colored triangles are all the individual sand samples that we collected. Each colored triangle corresponds to one of these plots over here with a pre and post Harvey sediment distribution. So this is the frequency distribution on the y-axis, and grain size on the x-axis, log scale in microns. The San Luis Pass, which is a tidal delta, meaning it is not fed by a river. Don't compare this to Brazos, where we just were. There's no river here. This is a tidal delta, where the sand is just being fed from the tides coming in and out of the bay. This tidal delta became significantly deeper and finer grained during Hurricane Harvey. So that's an observation, right? You can't argue with that. That's what the data shows. So we have to think about how could that happen. Remember that Harvey is not a hurricane here. It's not a big storm surge. It's rain. It's water pouring out of Galveston Bay and cutting through this area. And so what we are able to tell then is that as this eroded, after that it got covered with this fine-grained plume that's actually coming from here, or from Houston, or from Clear Lake, or Chocolate Bayou. Those fine-grained sediments that were washing through the city are what came out here and coated this delta. And so in this study, this is part 2 conclusions. And again, I cite the papers out here. These are these are students that have published these papers. Sediment sinks, such as the San Luis Pass flood tidal delta, are essential to capturing that sediment that was eroding out of the bay. If that delta wasn't there to capture those fine-grained plumes, the plume would keep going. Therefore, it is acting as a buffer. It's holding sediment for a while and buffering the system till the next time the erosion happens. And then it catches sediment and buffers the system. Mining in a delta like that, which was proposed and under discussion for many years, mining a delta like that would not only take the sand that was to be mined, but it would limit the capture of future sediment. Okay? So with that, let's go to our urban methods. This is our Hurricane Harvey study that we intended to do. So that one was just by accident because Hurricane Harvey happened. This is the Allen Parkway Bayou Dog Park, the Johnny Steele Dog Park. There's a whole bunch of sand there in what is normally a park and a bikeway, and that's why there's a bike in that photo. None of that sand was there before the storm. That is sand that accumulated during the flood recession. So for this part of the study, we have 2 methods. One is looking around, and we did more than just look. We actually took what are called sand peels, and we did this in conjunction with Jerry Kendall and his daughter, who is an artist. And in these sand peels, you can see these very nice descriptions of the sand. Notice the scales over here are in centimeters, but also in days, because we could tie these recessional deposits, recessional meaning they're being formed as the water is retreating and going away, and we can tie these directly to individual stages in the water retreat. And so we can see down at the base of these cores, maximum erosion. This is what we call day 0. Harvey's waters are at its peak. And then we get the coarse-grained sediments, and then largely fining upwards, not precisely. There's some variability in there. And actually, it's hard to tie these directly to the flood gauges in Buffalo Bayou because they were washed away. But we could tie them to the discharge records from the bayous. So when floodwaters were let out of Addicks and Barker, we can actually tie these individual layers to the floodwaters. So that's fun, that's interesting to see. but we also needed a quantitative measure of how much sediment moved through the city. So we used LIDAR. LIDAR is data to give us a DEM, or digital elevation model of the city. We were able to get LIDAR for 14 drainage basins and the flood-controlled reservoirs, Addicks and Barker, pre and post Harvey. So the post-Harvey LIDAR was collected immediately after, in part by the state of Texas and in part by FEMA, came in and did these. This is aero geophysical data. The LIDAR surveys were shot immediately after. The pre-Harvey data, of course, we didn't know we were going to need pre-Harvey data. So it's a little bit different in ages. It's more patchwork. Some of it is as old as about 5 years older than Harvey. Some of it is just about a month before. And so we're going to difference that data and look at pre and post Harvey DEMs in ArcView for every drainage basin crossing the city. It's a lot of work and a lot of data, but also with GIS you can do things like this. And so in this image, we're looking at a superimposed pre and post Harvey channel where the red or warm colors are showing us increase in elevation up to 6 meters in dark red elevation across that Harvey time period. And the blue or cool colors is showing us erosion or downcutting as much as 9 meters across the Harvey time period. This particular bio here, this is again Buffalo Bayou. I usually give talks, in the inner loop, so most of my examples are Buffalo Bayou, and this is across the River Oaks Golf Course. You can see that through here. And so we can see that there is distinct patterns of erosion across the outside bend, like you would expect across this flowing water, and distinct patterns of deposition or increased elevation in this difference in the inside bend of the bayou. So the measurements happened exactly like we might expect, and we did that for every bayou. How much sediment is there? Well, it's hard to get a handle on the numbers. Just like saying, 11 cubic kilometers of rain. Well, 27 million cubic meters of sediment, that's a hard number, okay? So instead we will compare it to volumes of the Astrodome, volumes of sediment moved during the period of Hurricane Harvey, maximum 90 days later. It's almost equal to the annual sediment discharge of the Mississippi River. This is the entire volume of Galveston Island that sits above sea level. And then if you like to get even bigger, we can see the Horn Mountain Field and the Pleistocene, a couple million years to recent of the Gulf of Mexico. That's a lot of sediment, even if you just compare it to astrodomes. So, to put this in context, again, we have to make some summary figures to put each of these individual bayous into comparison with each other. They're all different lengths. Every bayou that crosses the city has its own length scale. And so to put them into context with each other, these are actually in distance percentages. And so if you look at the x-axis on this diagram, you can see that it goes from 0%, meaning the mouth, up to 100%, meaning that it's headwaters, however long it is. And that allows us to compare each bayou to the other. And then in the different colored lines, you can see each individual bayou. It starts at 2 because one was a basin. And so Armand Bayou, Brays, Buffalo, etc., ending at White Oak. And we can see that they each, are carrying sediment down this way, but they have a break in slope where the average tidal limit is. This is something that, I've been a sedimentologist in Houston for quite a while. I never knew how far the tidal influence went before this study. Right up into the city, past downtown, the bayous are responding to each tidal cycle. Maybe not a lot, but they're feeling it. And so we can tie the sediment pulses that are deposited, and that's what's shown down here, to this tidal limit and the average break and slope. And so that we have sort of variable deposition of sediment along the percentage of the bayous, and then this distinct downstream increase once we pass the tidal limit into the bay. So, a little bit of geological conclusions here. One, alluvium accumulation. Alluvium is sort of the background sedimentation, not in the river, but around it. In the US, alluvium accumulation has increased over the last couple hundred years. That's largely due to farming and urbanization. That allows these big pulses to move down the system. Hurricane Harvey might have moved, that 27 million cubic meters of sediment, but it didn't scour it out of the base. If another Harvey happened tomorrow, it would probably not carry so much because we just scraped clean. We made a palimpsest surface because we removed that alluvium that had been primed for that storm. Second geological conclusion here is that the Houston-Galveston area streams are leaving stranded overbank sediment. In geology, there's a lot of questions about, does sediment move as a vacuum cleaner model or a conveyor belt model? You can think about what either of those would mean. And this is pretty clearly a vacuum cleaner model. The sediment accumulated and got swept out. So my third conclusion, before the big ones, is that Harvey mobilized about 27 million cubic meters of sediment across the Houston area. If we compare that to average annual sediment delivered to Galveston Bay, depending on what numbers you use, it was 6 to 50 years worth of sediment from the modern era. If we look back in time and calculate the geologic record, pre-anthropogenic, the change is even more, that Harvey was 30 to maybe 120 years worth of sediment compared to the geologic record. I didn't take the time to tell you that Addicks and Barker capacity actually decreased. The sediment that was sequestered in Addicks and Barker represents 1.5% of the total capacity, meaning the next time it rains, those reservoirs are that much smaller. We also broke these down, and if you look at the paper that is highlighted here, the natural channels retained their sediment, artificial channels induced bypass. That is not a surprise. If you're a civil engineer, you know that is the case. But in this particular study, we were able to get these big across the city budgets to really measure that all at once. So, what can we tell you about Texas sediment budgets by doing lots of studies like this? Well, sediment budgets, wherever you measure them, if they're from the modern, they don't accurately represent the longer-term budget. That Brazos budget, because it was only from 1929 to the present, is not yet representative of the longer term. And that short term is not representative of a year. These budgets fundamentally change. Storms are likely part of that. And this is affecting the depth of closure. When we talk about depth of closure, that's what we mean, where can you mine sand? Can you go out and safely dredge it without destabilizing the beach? In the Gulf, we might say the depth of closure is 8 meters or something like that. But if the sediment is coming in pulses, that 8 meters is also going up and down over time. So it makes it a lot more difficult to find a place where we can get sand, and that depth of closure then is highlighting the limited sand resources that we have here. So we'll end with that. That's my students, my Gulf of Mexico students, taking our sediment samples where we are studying this, and these are my other students doing our other work. Thank you. And I'll answer your questions if I'm permitted to. Yeah. Okay.
First is, how deep would a, thank you, how deep would a typical core be, and what would the, how long ago was the bottom of the core?
If you're talking about the Brazos River cores,
Yes.
so those cores, we never went past about 1900 or so, 1929, because we were only coring in the deltaic facies directly. So those cores were on the order of up to 2 meters. And if you're thinking, wait a minute, that's really, really fast for that delta to grow, you're right. And that's because the early phases of the modern Brazos Delta grew very rapidly by cannibalizing the old Brazos Delta, the natural Brazos Delta. So as long as that delta at Freeport existed, the modern one was growing very rapidly because you had this sort of pile of sand ready to cannibalize, to move. Once that was gone, the sedimentation rate has slowed down dramatically.
Right. Second question, what's the difference in particle diameter between a fine sand and clay?
Clays, so we use clays to be below 3.9 microns, and fine sand starts at 63 microns. Silt is 4 to 63.
Final question, are we running out of sand due to various concrete and other uses?
Depends on what sort of sand you want and where. That's a hard question. If you're talking about sand to nourish the beach in Texas, well, we've never had a lot. Texas's shorelines are not like Florida's. In Florida, you can just go out and dredge and dump sand on the beach. It's really easy. Because the depth of closure here, where sand is always active, it's always moving, below that, there is no sand. We are a sand-starved beach if you go out into the Gulf. So there's never been a resource there. If you're talking about building sand or fracking sand, those are different questions, and there's still some, sure. It's more expensive that way. Uh-huh.
You talked about artificial versus natural,
Yeah.
kind of channel
Yeah.
development. So when the new river path was dredged, right,
Mm-hmm.
that became an artificial channel. So did that kind of influence the results, or did you guys study how that might have
Yeah, that's an
influenced your
interesting.
results there?
That's a really interesting question because let's call that semi-natural, because they didn't pave it, they didn't clear it. The Army just sort of guided the river and let the river do some of the work itself. And so that's very different than where the bayous through the city are forced into their specific location. So if a large-scale diversion like that happens again, I think that would be an amazing opportunity to go study. But I think because that 1929 might be young for this geologic record, but it's too old for us to know in detail. Thank you. Yeah.
So a lot of the diagrams you showed had a lot of sand deposition happening in the attics
Yeah.
out to the west and also along the Buffalo Bayou.
Yeah.
Was all that deposition included in the 27 million?
Yes.
Okay, so
Yeah.
just that's all the sand that got moved,
Yeah.
but includes being deposited
Yes,
along
we
there.
tried to estimate the total amount mobilized and deposited anywhere inland of the shoreline. Yeah.
Thank you.
Yeah. Thanks.
Now it's on.
Okay.
Really interesting presentation.
Uh-huh.
I live out in Katy and work in Sugar Land, so I cross the Brazos
Yeah.
many times. And I noticed there's a lot of construction, like on the 99 bridge and I-10 over the Brazos.
Yeah.
Does that construction cause enough that you can see that? Or is that just such a short period of time that it's not really noticeable?
That's an interesting question to sort of make the budget. The quick answer is no, we can't see that. But I can also tell you why we can't see that. It's putting a lot of sediment into the river. But the Brazos is not ever a sediment-starved river. It always has enough sand around to carry as much as the water is capable of. And so the sand then, if it's mobilized by the construction, it gets dumped in and doesn't go very far until the next storm.
Okay, that makes perfect sense. Thanks.
Is it possible to go back in time with the study that you have done, at least the lessons that you have learned, and see were there Harvey-like storms in the past and what their frequency would have been?
Yeah. There are other people that do that work, and it's really interesting. So some of the experts that study sort of paleo storm records going back, let's say, 1,000 to 10,000 years, and look at storm frequency as well as storm intensity and patterns of landfall. So you can take longer cores along the coast, particularly in places like West Bay or Nueces or behind North or South Padre, places that are connected to the ocean but protected. Those are going to have the best continuous sedimentation records. And so taking a longer core through one of those inlets and then reconstructing the deposits over time. Some of the people that do that the most are there's somebody at University of Southern Mississippi. There's actually somebody in Massachusetts that works here in the Gulf. So I don't do that myself. The answer, though, that maybe you're looking for is, have hurricane landfalls noticeably increased in number or intensity? And the answer is probably. Okay. We need maybe a little bit longer a record still to answer that definitively. So the records so far suggest that. Okay.
I was wondering about the effects of Harvey and all this water cycle and transport. What effect it had on the safety of the drinking water supplies? Because temporary, I know we had a lot of mishaps with wastewater plants being overflooded and everything, but okay, that goes away. Longer run, what does it have to do?
I don't know. The most relevant story I can answer that with is that I know in Lake Houston, of course, the inlets where water was collected did get clogged up. And so there were sort of temporary dredging needed for water inlet areas, just because of storm debris getting into those intake systems. So that was a very short-term issue. And of course, the ship channel was closed. You might all know that. So there was so much sediment accumulating in some places that work actually had to stop until that sediment could be dredged. And the drinking water inlets, at least in some places, were like that as well. No. Okay.
I've got a couple questions.
Sure.
So there's a water model of how to handle all the sediments and making sure we're draining right in Houston. Someone manages that. Do they need chemical engineers? Is there, or who is? I'm wondering if there's a place for fluid flow, which chemical engineers do a lot of. That's one question, and I forgot the other. I'll think in a second.
So you're asking, is there room for more people to come work on
Yeah,
that?
just in the whole drainage system. I'm wondering if there's a need there.
Yeah, I think
Is there a model that handles all this, everything?
I think
Yeah.
there really is a need. I think you're absolutely right. I started this shortly after Harvey, within a month or so. I started working out at the San Luis Pass because I'm a coastal person. And I was invited to a working group. And there was a representative from the Port Authority and from the Houston Galveston Council and from FEMA and Texas Parks and Wildlife and Houston City, and Harris County Flood Control District and the Houston Galveston Subsidence District, right? So everybody sent a rep. And I guess I was the academic rep. And it was called something like the Soils Working Group. I didn't name it. And it was, this group of people saying somebody needs to get a sediment budget because no one group was going to worry about it. FEMA would take care of people, and the subsidence district would measure subsidence, and so forth. So I said, well, I can make one budget. And so there really is no broad-scale integration, and I find it shocking. So I think there's absolutely more need.
Yeah, I've thought about quitting my job to just solve the problem. It's a hydraulic mess that
Yeah.
somehow I was thinking someone has that, but
No.
I guess not. The other question I had is, so I live near Brays Bayou, near the University of Houston, so just curious, you were saying the certain sand is done, like it's not gonna, there's a certain level, is what I'm understanding, that's not gonna move. And so if there's another hurricane, it won't, are we better off or we need to dredge it the whole way? Yeah.
We're worse off in some ways and better in others, right? If you're interested in getting a tanker up the ship channel, you're better off. But if you're living here, you're worse off, okay? Okay. Okay. Anybody else?
All right, thank you, and
Okay,
thanks to
thank you.
everyone for coming. Again, I'll put my PDH credits up here and then a couple other things. Sign up for April 4th. We're going to have a good event at the Black Lab, and there's lots of other things going on. SBTC this year. We're planning to do it in October. We're going to do it ourselves, and we're looking at a couple venues, maybe at UH or at St. Thomas, and then maybe some others. So we'll know that in the next month, and then we'll be letting you all know. So thank you, and have a good night.